Because it's birthday, a takeaway from mine. She wanted to have a style family birthday thing, which is that gonna be on the same day? Well, I mean, I don't really care much about it. It bothers me. It's like, I mean, specifically though, it has to be for me. Your day, right? That'd be great.
Two questions.
Right.
Wrong class. All right, here's discrete. So I hope you guys turned in your homework assignment. Okay, some people came see me today, and so I know you guys are on task. Okay, trying to get it done. How was the homework assignment? Was it okay, kind of easy, kind of hard, or somewhere in between?
Most of it seemed pretty easy, just when you got down to like the actual kind of math part.
But the entire thing is actual math part.
Yeah, I guess.
Okay, so all right, but there are multiple ways to get this homework assignment done. There's no just one way to do it. But the principle is the same way. It's just when you get to the algebra part, which way do you which path do you want to take? So what I'll do today is I am going to talk about that first. So I will do the homework assignments just so that you know the answer. And then we'll continue to talk about probability and a new homework assignment, with probabilities. Okay, but this one is fun. Okay, you guys are trying to help. You guys will help me figure out, something. So we'll go ahead. we'll deal with that later. All right. So the theorem that we are trying to prove is the first part of the homework assignment. Okay, and I did specifically said in class, there's no need to use quantifiers in your answer. So that means, if you look at this one, you just forget, for all x, for all y, for all p, you basically just say that, okay, by definition, p is the product of x and y. X is a natural number, y is a natural number. And that has to imply that x squared is less than or equal to p, or y squared is less than or equal to p. Which is basically the same thing as saying x itself is less than or equal to the square root of p, and y is less than the square root of p. Or, I should use or. Okay? So that's just two ways of looking at the same thing. So now the question is, if this is actually a theorem, if it is actually true, how do you prove that this is actually true? And we are going to use proof by contradiction. And that's the whole point of your homework assignment, is to practice proof by contradiction. So what I'm going to do is I will use a text editor to do this. So it's not going to be in the math notation, but it's close enough. I'm pretty sure most of you can read just the text portion and understand what it means in math equations. All right. So the first thing we need to do with proof by contradiction is to invert the statement, to basically do the negation of the theorem. And then we are trying to prove that the negation of the theorem will lead to a contradiction. That's the whole point of proof by contradiction. So what we want to do is to extract the theorem part. So the theorem part is basically just saying p equals to xy implies that x squared, it implies x squared is less than or equal to p, or y squared is less than or equal to p. This is the original theorem. And in order to prove by contradiction, we have to negate it first. Okay? So the negated theorem is exactly the whole thing. So I'm just going to copy and paste the entire thing and just put a knot around the entire thing. I cannot easily apply negation to an implication. So the first thing I need to do is to convert the implication into a negation and an or. negate the first part and then or the second part. Okay. I keep the negation on the outside, but in the inside, I basically negate it and go like not the case p equals to xy, or and then the entire second part. So the entire second part goes from here to here, and I just kind of copy and paste it like that. Are there any questions about what I just did?
Is it all right if we list the laws that we're using alongside the steps that we're at?
Yeah. Yep. So if I want to name this particular step, this is because of by definition of implication. Okay. Are there any questions at this point? Okay. So the next step is I can now apply De Morgan's law because I have a negation on the outside, a disjunction on the inside. So now I can apply De Morgan's law. De Morgan's law basically says you can distribute the negation that is on the outside to each component in the inside, but you have to change the operator of the or into a conjunction. So disjunction becomes conjunction. So that means I get to keep p equals to xy because that one is going to get double negation because it already has a negation inside, and now I have to apply a negation or distribute the outside negation into the inside. And then we have an and here. The entire thing of the and is going to be the negation of this part here. So I'm not going to do two De Morgan's law at the same time. So I will just do it one step at a time. Okay, there we go. So this one is by De Morgan's law. De Morgan's law. And also double negation. Double negation, you don't have to name it because it's pretty obvious. So if you forget to mention double negation, it's no big deal. All right. Question? Yep.
You have an extra parenthesis on the end. Yeah.
Did I? Okay. And it's only here because I used De Morgan's law to take out the other open parentheses. Thank you. So now, oops. So now we have p equals xy. Oops. P equals xy. And now I reapply De Morgan's law. And this time when I apply De Morgan's law, it's going to say x squared is greater than p, and y squared is also greater than p. And this is by De Morgan's law for one thing. And I changed the operator. So instead of saying it is not the case that x squared is less than or equal to p, I just changed it to say that x squared is greater than p. Are there any questions about this particular step? So this is De Morgan's law, and I also used a little bit of algebra. Okay, changing the not less than or equal to just greater than. Is that okay? Yep.
Why did you change the second?
Why did I change?
Y squared, why did you change that as well?
Because the negation, because when you apply De Morgan's law, the negation on the outside of the disjunction is distributed into the inside. But when you say not x squared is less than or equal to p, it is the same thing as saying x squared is greater than p.
But I'm asking for the y though. Why did you change the y?
Why did I change the y?
From less than or equal to greater than.
Yeah, because isn't it you're making
Because I'm using De Morgan's law to distribute this not to both this component and also this component. All right? Okay.
No, you only did for the first one. Yeah.
All right, so when we get to this point, I think most people kind of intuitively can tell that this is a contradiction, okay? But how do you actually say that, hey, something is wrong here, okay? The key is to make use of p equals xy, and there are several ways to do it. Some people use division, but if you use division, because x and y can both be natural numbers, they can be zeros, so you have to break it up into two cases. What if x is 0 and what if x is not 0? Because if you divide both sides by x, you have to kind of deal with that. The other way to do this is to do it by multiplication. Okay? So when you do this by multiplication, then you can do something like this. Okay? P equals to xy, has to stay here. So everything that we already know gets to stay, but we can also say something that is implied by all of these things. Okay? So I can just say that, hey, if all of these numbers are non-negative because they're all natural numbers, this number times this number has to be greater than this number times this number. Is that okay? All right, so we can combine those two and say x squared times y squared. Okay, I'm just going to use a multiply here just to be clear, is greater than p times p. Is that okay? Does it make sense? Because this is one of the things you can apply in equality, where you can say if all numbers are non-negative, a is greater than b and c is greater than d, implies that AC is greater than BD. Is that okay? Now this is what I choose to use, okay, because I don't have to deal with a division by zero case and make a separate case out of that one. But if you use that one, that's okay too. But this one does not involve a special case for zero. So when you get to this point, then the next stage is to rearrange things a little bit using algebra. So I'm just repeating the first part here. But the second part, which is x times y, because multiplication is commutative, I can now rearrange the xy's a little bit. So this one becomes x times y times x times y. Is that okay? Does everybody see how x squared times y squared can be re-expressed as x times y times x times y? Okay? And that is greater than p times p. And I'm just going to be a little bit lazy and just copy and paste the most part of this because it doesn't change. Okay, so when you get to this part here, you can now apply the associative law of multiplication by reordering the multiplication. So x times y is one group, and then the other one is also x times y is the other group. Now I am really trying to do this step by step at this point because it's all algebra. Okay. And that, by definition, x times y is p, x times y is p. So we have p times p is greater than p times p, and that is our contradiction. So one last step is to say this is zero. This is contradiction. Cannot happen. So are there any questions about this particular proof? Because this is not the only way to do it, it's just one of the many ways to do it. Yep.
I was talking to some people, and then they said that they didn't add the zero to the end of it because the zero showed resolution instead of a contradiction itself. So should we have the zero on there to show this a contradiction?
You really should say the entire thing is a contradiction, which means the entire thing is false. Or either you can put a zero here, or you can state, using a sentence and state that this is a contradiction because this thing is false, regardless of which value of x, y, and p you choose.
Okay, so as long as we state where the contradiction was, we'll be okay.
Correct. But you have to get to at least p times p is greater than p times p, or x is greater than x, or y is greater than y. Something that is obviously a contradiction, something that obviously cannot happen.
I used the division, but I used the special cases where x
Okay.
was zero. So.
If you get to x is greater than y and y is greater than x, I will take that also as kind of clear enough as a contradiction. But anything not that obvious, probably will get some points taken off. Because you kind of have to get to the end and let me know, okay, this is obviously a contradiction.
I'll take that.
Okay. Are there any questions about this proof? Any? No? Alrighty. Okay, so if there are no questions about this, I will leave this one in the editor until the end of the class, and then we'll go ahead and start on a new homework assignment, which is closely related to something that we already did. Okay, so remember last time we talked about lotto. Okay, and hopefully most of you still remember. How many people went out and actually bought lottery tickets anyway? Okay, so this is a new homework assignment. You cannot quite see it yet because it is still hidden. So let me just unhide it first. So this way, for those of you with a laptop or a tablet, you can actually read the description on your own devices. Unhide module. Save and display. There we go. All right. So if you read the whole thing, it's kind of funny. So I'm trying to raise money to send my own kids to college. So I'm going to run my own lotto game where it is legal, and this is these are the rules of the lotto game. Okay. So I issue unique lotto tickets. Each ticket can only be sold to one person. So this is a big difference between my lotto game and the California lotto game. Because in California lotto, they can print as many tickets as there are people or as there are purchases of these tickets. Which means, you can't end up with multiple people winning the jackpot with California lotto. With this, it's not. Okay, with this, only up to one person can win the jackpot. Okay, because for each possible combination of numbers, there's only one ticket. Okay, so this is a main difference. When you analyze this makes a big difference. Each lotto ticket is going to cost $1. Okay, which is about the same as the state lotto. A person can purchase any number of tickets. So if somebody figures out, oh, I only need this much money to buy all the tickets, that person can potentially buy all the tickets. The lotto drawing is done as follows. Okay, there are 6 out of 30 balls labeled 1 to 30 drawn out of the tumbling bucket. Okay, so 6 out of 30 is the first part. And then there are also, another bucket containing colored balls. Okay, so in this case, 3 out of all 3 balls will be drawn from the tumbling bucket. So in the first case, it's a matter of combination. In the second case, it's a matter of permutation, because I have to say 3 balls anyway. Okay, if I just say, okay, it depends on which 3 ball you pick out in a ticket, everybody's going to win because it's going to be the same 3 colors. So with the second set, it is all about the ordering. Okay, is it red, green, blue in that order? Is it green, red, blue in that order? Is it blue, green, red in that order? There are 6 possible permutations when you are trying to arrange 3 things in different ways. Okay. So the way people win money is like this. Anyone who has 4 out of 6 matching numbers in any sequence wins $12. Okay. If the ordering of color balls also match, the price is up to $60. Yep. Mm-hmm.
Where there's 3 out of 3 bulls, so that means there's 3 bulls in the cage and you draw all 3 of them out, or is that?
You draw those out one by one, but then it depends on the sequence, the ordering of those balls.
Oh, that's
becomes the important part.
So
the ordering of the color is important, but the ordering of the numbers is not important. Okay. I'll give you guys some examples afterwards, but first I'll describe the rules. Yep.
You left the answer out in the rating criteria.
I did?
Yeah.
Okay, so that means I have to change it a little bit.
Oh, you should. I didn't even look at it.
Well, actually, that is not entirely true. If I leave it the way it is, some people will definitely get beaten. I'm not going to say why. I did make some changes already. And then the second one is 5 out of 6 people. Okay, if someone has 5 out of the 6 winning numbers, those people will win $1,500. If they, on top of the 5 out of 6 matching numbers, if all the colors are also matching in the same sequence, then those people will also win they will win $7,500. Okay. Anyone with all 6 matching numbers in the sequence will win $120,000. If on top of that the colors are also matching in the right order, then the jackpot is won. So given these rules, not counting the jackpot, on the average, is TAC running this game is going to make money, or am I going to lose money? That's the question. Okay. Prove that and prove whether I'm going to win money or lose money on the average. Assume that all possible tickets are sold. How much money, not counting the jackpot, does TAC has to come up with to pay all the prices? Compare that to the money raised by selling all the tickets. In other words, one easy way to do this analysis is to say, okay, let's assume all the tickets are sold. Okay, so every single ticket is sold. So that means, there will be a fixed number, known number of people winning every single prize. So you add up, all the money that I have to pay off, because that's going to be the money that I have to have available. The jackpot is basically, whatever is remaining or something like that. And then you have to compare that to, how much money I'm going to gain because of the $1 per ticket. Yep.
I'm a little confused about the jackpot. How much is it?
The jackpot is going to be, that's a good question. I'm pretty sure.
Because it is the remaining sum that you never make money.
Well, it never really said anything about the jackpot, so what are the chances?
We're excluding it from all the calculations. So
Yes,
it
we
doesn't
are
matter.
excluding the jackpot from all the calculation. What are the chances of winning the jackpot? Express your answer in the form of 1 out of n on the average, and show all your steps. In other words, I'm not, telling you guys, how the jackpot is done. I'm just doing the calculation based on the other prices.
Can you scroll up just a little bit so I can see the top?
Oh, so. Sure.
No, the other one.
Up.
So I can see the top of the.
Oh, there we go. Now, typically the jackpot is, if no one wins the jackpot, it gets, lumped onto the next round, and it just keeps, growing increasingly. But if I sell all the tickets, there won't be any rolling into the next round.
So we're assuming that you sell every ticket, but we're
Right.
just taking that one ticket that would be the jackpot and discarding.
Let's say he
it from-
kept it for himself.
Yeah.
It's a rigged one. But if people are going to win, they're just not going to get the jackpot, assuming one exists.
Well, the jackpot is just
Yeah.
going to be breaking even, because if I sold all the tickets, I want to make sure that I don't lose any money. So that means, the jackpot is just going to be whatever amount of money I have left in the entire thing, so I'm not going to lose any money.
Well,
But I'm not putting it in the calculation. So in the calculations, it's all based on the other prices, everything excluding the jackpot.
But your kids are not going to college.
They're going to this college. Yes. What? There's nothing wrong.
Yeah, there's nothing.
You don't need a loan.
So, I mean, I don't know if I'm just lost. But,
Go ahead.
So is the first calculation is figuring out the number of possible permutations? Like, we have to figure out how many possible tickets there are to be sold. Since there's...
Well, since the answer is already, in the grading criteria, and I'm pretty sure most of you are already there taking snapshots just in case I take it off the internet. I know you guys are smart. So how do I know? Because, I think 8 people got A's in exam 1. About half of the half the class got B's, half the class got C's, and then the rest are D's. So I think that's pretty good in general. I think that's pretty good. 8 people got A's, and then about half the class got B's, and then another half got C's. That's actually a pretty good distribution for this class. So that's why I know you guys are smart. So maybe I'll just kind of work this one out in class, and I'll give you a different homework assignment. I think that's probably the best way to do it. 'Cause instead of having you guys copy and paste, that's. All right, so let's do this analysis. Okay, the first one is how do I match 6? Okay, 6 out of 30. Okay, so what you need to do. This is also closely related to what I need to talk about today, which is kind of formalizing what we talked about last time. Okay. Which is the probability thing, okay? So how many tickets is possible with this particular arrangement? Let's do the calculation. I'm going to do it on the projector here. Okay, so I'm going to take this out, because that's old stuff. So now we'll work on the quote-unquote homework assignment, which is not really your homework assignment. Okay? So we have 6 out of 30 numbers, and this time we are looking at combination. Every time you look at combination instead of permutation, which means the ordering is not important, then you basically choose, you use one of the other notation. There are at least 3 notations to indicate this number. One is a C, and then 30 is the total number of things, and you're choosing 6 out of it where the ordering is not important. This is one way to indicate that number. The other way is a parentheses with 30 on top, 6 on the bottom. They mean exactly the same thing, okay? This is exactly the same, which if you look at the calculation, is 30 factorial divided by 6 factorial times 30 minus 6 factorial. That's basically how you compute combination. All spreadsheet programs has a combin, C-O-M-P-I-N function to calculate this. So there's no need to use your own calculator. I would just do everything with a spreadsheet. Okay? So that's the total number of tickets just because of the numbers. But on top of the numbers, I also have the ordering of the colors, right? But that one is a permutation. It's not a combination, it's a permutation because ordering is important. So I'm choosing 3 out of 3 things where ordering is important. Okay? And that turns out to be just 3 factorial in this case. So are we doing okay so far with the notation? Combination where ordering is not important, permutation where ordering is important.
Excel equivalent for that?
The Excel equivalence of this one is combin, C-O-M-B-I-N for combination. This one is permutation, is permut. Okay. So if you use a spreadsheet, P-E-R-M-U-T is doing the permutation. Is that okay? Okay. Yep. Why is it? It's 3. I'm choosing 3 out of 3. But ordering is important. Okay, but we can also look at the general equation. If you are looking in combinations, you have n to choose from. You're choosing r out of n. Okay, so n is the total number. R is what you're choosing. This is the number of things you're getting out of n. This is basically just n factorial divided by r factorial times n minus r factorial. I'm doing this one on the whiteboard because it's just quicker for me to write it out on the whiteboard instead of using a text editor. It's also in my notes, so if you don't copy this, it's fine. It's on Moodle already. Now with permutation, it's a little bit different. Okay, you have n items to choose from, and you're picking r items out of n. Okay, but this time the ordering is important. Okay, this one is n. Let's see, it's n factorial divided by n minus r factorial. The division of the factorial is just to take care of the tail end, because, okay, we can look at some examples, okay? Let's say we are looking at 3 possible things. We're picking out of 3 things, and we're only picking 2 out of 3, okay? So the question is, how many different ways where ordering is important can I choose 2 things out of 3? According to this equation, plugging in, it is 3 factorial divided by 3 minus 2 factorial, which is 1 factorial, which is 1. So there are supposed to be 3 ways to do it. 3, I can enumerate all the possible cases. Let's look at A, B, and C. These are the things that I'm choosing from. But I can only choose 2 items out of these 3 where the ordering is important. How many ways can we do this? Yep. Oh, that should be 6. You're right. Okay, sorry. That should be 6, which probably will be clear when we actually work out the example. So we have AB, BA, AC, CA, and then we have BC, CB, 6. Is that okay? Because we have, the other way to look at this is we have 3 possible choices for the first item, but once you have selected the first item, we only have 2 choices left for the second item. So that's why it's 3 times 2. The 1 is lost because we divided by 1 factorial. Yep.
So I'm positive this is the exact same question you just answered. But I'm sorry, I just have to say this out loud. So it seems like the only difference between P and C is that R factorial disappears.
That is
in the
correct.
denominator.
The R factorial is in this case, and the R factorial is gone in this
Yeah.
case. Do
And
you know
so
why?
Is that what all that explanation was?
Yes. No. Well, no. This is just an example to illustrate, to demonstrate how it works out. Okay, it's an actual example of picking 2 out of 3 items where the ordering is important.
So
Okay.
what's the theory behind the R disappearing?
That's a good question. So the question is, why do we have this R factorial as part of the denominator when we calculate combination? We talked about this last time, okay? Just a little bit, okay? But but the reason why there's a factorial here as a denominator, because there are R factorial ways to rearrange R items, so that so out of R items, okay, out of 2 items, I have 2 ways to arrange it. But if the ordering is not important, then you have to basically say, oh, these 2 are the same thing, these 2 are the same thing, these 2 are the same thing. And that's why we have the R factorial in combination.
Okay, so that R factorial basically represents, in the combinatrix, it represents the fact that we aren't concerned with the order.
That is correct. We are canceling the duplicates because of permutation. Yep. Absolutely. So with this particular question, this is a combination thing. So that means, I can't really do this, easily because I can't do the superscript and the subscript together. I can show you what it looks like in LaTeX, which may or may not be helpful.
We could just
So instead, I'll do this instead. I'll do the C open paren, 36 to basically mean we're choosing 6 out of 30 items, and this is a combination. Is that okay? The colors are 3 out of 3, so 3 out of 3 colors, but this time it is the permutation that we are after. So this is P33, which means we are choosing 3 things out of 3 where ordering is important. Is that okay? But these two particular parts of a ticket are completely independent. In other words, when you look at a lotto ticket under these assumptions, the 2 parts, the 6 numbers and the 3 colors, are completely independent. And that means when you want to look at the number of possible tickets, you're looking at the product of these 2 numbers. Is that making any sense? Okay, so I can give you one example. So let's just say that the 6 numbers out of the 30 is 1, 2, 3, 4, 5, 6 for one particular ticket. But out of this particular number combination, I can end up with 6 possible permutations of the 3 colors, right? Because I can have RGB, RBG, GRB, GBR, and then we have BRG, and then BGR. Same number, same 6 numbers, but now we have 6 tickets because of the colors. Is that okay? Yep.
Is it a product of probabilities or product of just those 2 numbers?
No, that's not probability. That gives you the total number of possible tickets, which is a very important number because everything is going to be relative to the total number of possible tickets. So this is a really important number, but by itself, it is not a probability. Okay, so the total number of tickets is C66 times P33. we go. And using a spreadsheet, it's easy to calculate. I'm just going to add a new sheet here. So we have combin 36. This is the number of tickets. Well, this is the number of combinations of 6 numbers. Choosing 6 numbers out of 30. And then we have permute, or permut, 3 out of 3. We already know that's just 6. Then we are looking at the product of these two. So this is the actual number of possible tickets. So I just copy this, paste it into my notepad here, and that's just the number.
So that's how much money you'll make, assuming.
That is correct.
Ticket.
Yep,
So
that is because each ticket is $1. So if I guarantee to sell all the tickets, that means I'm gonna make this much money. This is my income.
So now you gotta figure out what are the different combinations of.
Right. So
what
now
people
we
can
need to
win.
figure out, how many people or how many tickets will win this prize, how many tickets will win that prize, and do all the calculations. Okay. It's not bad. Okay. So I know, because I only sell 1 ticket per, unique, configuration. So I know this is the total number of tickets that I can sell. So now the question is, out of this many tickets, how many of those will win the first prize, which is matching 4 out of the 6 winning numbers, and not without the correct ordering of the number, and then with the correct ordering of the numbers. So let's try to figure those out. Okay. So let's switch back to the browser. Oops, I just passed it. There we go. So the first prize is, matching 4 out of the 6 winning numbers, but not with the correct color ordering. Okay, those people are making $12 each. Okay, so we'll go back here and figure out, okay, so how many tickets will win $12? Okay, so I'll just say $12 tickets. Okay, so these are the ones that will win $12. So the net gain is $11 on each ticket. All right, so how do we calculate this number? Well, we know that out of the 6 numbers chosen, 4 are the winning numbers. Okay, and we know there are 6 winning numbers. So now we want to find out, okay, so how many ways can we choose 4 out of 6 winning numbers? Yep.
Wait, so if you sell all the possible tickets, then isn't there there's one jackpot, then you sell all the possible tickets, so then someone's going to win the jackpot?
Yes. So the only way I can afford to send my kids to college is to make up the rule of, with the remaining money after paying off all these extra prices, the jackpot is going to be 75% of whatever money is left. So I still make 25% out of the remaining portion.
Assuming there is a remaining portion.
Exactly. So the calculation is now, saying, okay, do I have anything left? Or is it a negative number, which means, just paying off these other prices, not even the jackpot, I'm going to go bankrupt. I'm sending somebody else's kid to college.
Or unless you don't sell all the tickets, which means that there's not a guarantee that someone will win the jackpot.
Correct. If I do not sell all the tickets, then it becomes a real probability thing. Because if I only sell 1 ticket out of these many tickets, okay, out of the probabilities, what are the chances that I'm going to make money? But it's going to be the same number. That's the thing. It is going to be the same number. Once we figure out, assuming we sell all the tickets, we'll know the answer. Okay. Okay, so let's get back to the $12 tickets, or the tickets that will win $12, okay, with a net gain of $11 per ticket. Okay, the first thing we notice is we are choosing, out of 6 winning numbers, we only want 4. Okay, so this number becomes important. The combination of choosing 4 out of 6 is now important, because out of the 6 actual winning numbers, these tickets need to match exactly 4 out of those 6. And the ordering is not important. That's why this is not a P, where the ordering is important. This is a C, where the ordering is not important. Is that okay? All right. But then that only accounts for the winning numbers. So now we have to look at the non-winning numbers. The non-winning numbers is also a combination because as far as the numbers are concerned, ordering is not important. So they're all combinations. But now we have to say, but how many numbers are we choosing from? Now you have to remember 6 is the winning numbers, and we have 6 winning numbers. So now we have to say we should not be looking at 30 anymore, because out of the 30 numbers, 6 are already winning numbers, which are already accounted for by the first part. So out of the 30 numbers, only 24 are quote-unquote non-winning numbers. So we are choosing out of 24 in this case, and we're only choosing 2 out of 24 because we're only choosing 2 non-winning numbers out of the 24 non-winning numbers. So this accounts for all the tickets. Well, this accounts for all the combinations of numbers. But remember that this one cannot have a matching ordering of the colors, right? So how many ways can we arrange the colors excluding the one that is actually winning? So you have to multiply again, but this time it is the permutation of choosing 3 out of 3 colors minus the one that is actually the one that matches. In other words, we already know the permutation of choosing 3 out of 3 is 6. So this is just 5, because out of the 6 possible ways to order the 3 colors, one is winning, which is not getting $12. That one is getting $60. So out of the ones that are not matching the ordering of the colors, there are 5 of those.
Okay.
Is that making any sense? Okay. So we want to figure out what this number is. So we'll just go ahead and go back to the spreadsheet. 6, 4, 24, 2, and 5. So let's go back to the spreadsheet here. Okay. So these are the $12 tickets. So we are looking at combination 6 out of 4, 24, 2 out of 24, and 5. Okay, the 5, remember, it is because of the permutation of 3, 3 minus 1. Okay, so if I want to make sure that this is actually making sense like that, I will do it like this and put parentheses around the last part. Okay, so 20,700 tickets will basically win the $12 prize. Okay. And this is the actual money that I have to pay, and the product of these two is going to be the money that I have to pay off because of the $12 price. Is that okay?
Although you have to pay $11.
Say again?
Are you paying them $11 or $12?
I'm paying them $12 because I get the $1 already, so I'm going to pay them $12. This is the amount of money that I'm making. This is the amount of money that I'm paying off for the people who win that prize. Yeah, for the $12 ones. The $60 one is easy. Whoops. $60. Okay, so the $60 tickets. $60 tickets, or the ones that win $60, is going to be about the same number, except we have to tweak a few things here. Just one. The only one thing we have to tweak is there's only one color ordering doing this. So that's why I changed the permutation of 3, 3 minus 1 to just 1. Okay. There are 4,000 tickets. Each one is making $60. So the product is just that number. It's the same number because the price without matching the color ordering is exactly 1/5 of the one that has the color matching. So that's why they're exactly the same number.
Can you show me what you changed again?
Sorry?
Can you show me what you changed again?
Instead of this part used to be permute 3, 3 minus 1, now it's just 1. because there's only one winning correct ordering of the colors. But there are 5 ways of the wrong ordering. Okay. All right. So the $12 and $60 are accounted for. Now we are moving on to the $1,500 and $7,500 ones. Okay. So 1,500, and that equation is going to be very similar to this one, except we have to tweak. We are choosing 5 out of the 6 winning numbers. We are choosing 1 out of the 24 non-winning numbers. And the permutation part is the same because this time I still don't want it to have the correct color ordering. So that means out of the 6 ways of ordering the colors, 5 would fall into this category because 1 is going to fall into the next one. Yep. Okay. All right. And I really like the spreadsheet format because it really shows the not only how the numbers are, how I come up with the numbers, but also it does the calculation right away. So press the enter key. 720 tickets will have a payoff of $1,500. So the product of that is going to be $1.08 million. So the next one is going to be the same because these are the $7,500 tickets, where the number is going to be about the same as this one, except there's only 1 correct color ordering. So instead of 6 minus 1, it is just 1, but each one is going to win $7,500. So that means the actual total amount is going to be exactly the same. Are we still doing okay so far? You guys can see that I'm getting pretty close to not actually making any money. All right. So the last one is matching all 6 numbers, but not having the correct color order. Okay, so we'll work out that one. So copy and paste again. This time it is the combination of choosing 6 out of the 6 winning numbers and choosing none of the incorrect or non-winning numbers. That's fine, okay? Choosing 0 out of 24, you can actually plug that into the equation and figure out what it is going to give you. Okay, because we basically just have the 0 as the number at the bottom here, or if you look at the more general equation, it's over here. So when r is 0, r factorial is 1, because by definition, there's only one way of choosing nothing out of nothing. But then you have n minus r. R is 0, n minus r is n itself, so you have n factorial divided by n factorial. So when you choose nothing out of any number of things, there's only one way to do it. So there's nothing wrong with entering the equation as, okay, let's pick 0 things out of 24. It will just give you a number of 1. Okay. And I still have to make sure that I fix this part here. This is the, once again, the permutation of choosing 3 out of 3. And then remember to minus the one that has the correct color ordering. Oh, I have a misspelling here. There we go. And I'm losing. Nope, that should be good. That should be good. Okay, so there are 5 tickets winning that particular prize, and each one is paying off $120,000. And I have to pay off $600,000 out of those. So when you add up these numbers, that will give you an idea of how much money I have to pay, not counting the jackpot. Now that number is pretty close to this one, okay? So when you look at the difference between these two, we are looking at 306-ish, $1,000, okay, which is going to be quote unquote the jackpot.
Which is the jackpot itself.
Yep, but that depends on how I want to structure the payoff for the jackpot. Because if I say the jackpot wins, 75% of whatever is left, then I keep 25% of that.
Or if you set it up to do payment plans, you still get to keep
Payment
the jackpot,
plan.
but you pay them once a month
Well,
for 30
he
years.
still loses that, so then he'll have to think that his children graduate.
Yeah, but if he keeps running it, he can die before he runs out.
Or they can die,
That's
and then
correct.
you don't have to pay it.
Yep,
And then,
George.
And then you still have to pay the bank because you lend the money from them.
Exactly.
Actually, he already has the money. They paid in advance. So he
Exactly.
has cash.
They
I got
paid
the
it
cash
back,
to
but-
begin with.
All right.
I do have the expenses of, actually printing the lotto tickets, but if it's done online, there's no actual paper to distribute.
No
So
paper
something it's
trail.
not. I mean, you could put like with 300, assuming no one wins the jackpot, you could put through a couple kids to college with that.
Or if you rig it so that way one number is going to be out of the jackpot
Well,
and use that to your advantage to pick the one that's
Well,
most
just
likely
do
to
this
win.
like once a week for a year, and you'll shave off enough if you do it. It's feasible.
Exactly.
Pay out more money than you receive. Would that mean that by playing the game, you're more likely to win money than to lose money over time?
That is correct, but that's not how it is at this point. At this point, it is not bad, okay, because the quote-unquote payoff is actually, I would say it's about 90%. It's 90+% of the. You have a 90+% of actually not losing that dollar. Is that making any sense?
Which would make your game pretty great to play.
Assuming everybody
I
plays.
said it would make your game pretty great to play.
There'll be more people playing it.
If everybody was picking
So I
the
can
same
sell
numbers.
ad on the side of the actual lotto site and make more money from the ad than the lotto itself. Yes. Yep.
Just curious, what is the probability that someone's actually going to win something?
Oh, well, let's figure that out. Okay, so what is the probability of actually winning something? That is going to be this number. Okay, so let me just kind of write it here. The probability of winning something, anything. Okay, so that is going to be. Okay, I'm going to use an equation here.
I'm about to say, yeah, can you do that with just symbols?
It's going to be pretty easy because it's going to be the summation of all of these. Because this, no,
Not those ones.
no, that's not the number.
Those
Okay,
columns.
there's no easy way to do it because
Yeah,
these
sure.
are actual numbers.
Can't
I
you
can't
use
do that.
the value from it?
Yeah, I can do a control click.
Yeah.
That's what I'll do. So click, 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 click,
+1.
and then +1. That is going to be, let me just scroll it up so that people can see it here. There we go. So this number here, the summation of 20, 700, 4140, 720, 144, and 5, and then the +1 for the jackpot. This is the total number of tickets that are quote-unquote winning tickets, okay? Some can be winning only $12, and others can be winning up to maybe 200 something, $1,000, okay? But this is the total number of tickets that are winning tickets. And then you have to divide it by the total number of possible tickets to give you the probability. Because these are the ones that are winning, okay? These are the, discrete individual ones that are winning. But you have to divide it by the total number of tickets, which is this number, this number here. Oh, I forgot to close, or there's a mismatch of parentheses.
Yeah, you need a closing one.
You get it, yeah.
Closed one unnecessarily.
You didn't close the last one.
Yeah, I think it did it correctly. Yep. So it did it correctly. So your chances of actually, so the probability of you getting a winning ticket is less than 1%. It's a little bit less than 1%. However, if you play enough times, the chances of you not losing the dollar is actually pretty high because over time, you will win $12, $60, and so on. So on the average, because what you do is you look at the total payoff, right? So out of selling all possible tickets, out of 3.5 million tickets, I end up usually paying off $3.25 million. Okay, so that means overall speaking of all the tickets, each one is only losing 10 cents or so. Is that making any sense?
Yeah.
It's general.
Well, which
I
means you
mean,
should not be
right,
playing,
so-
because you're playing to lose.
So playing this game, if you play enough times, your chances of actually losing a lot of money is not that high, because you always win something.
So, how much money would you lose if, let's say, not everybody played, but everybody who played somehow got every single one of the winning tickets?
So yeah, then only
And-
that number of winning tickets, that's the number of Ilubai tickets. And,
then
all of them are winning.
Would the jackpot have to pay you because they get 75% of the winnings? But if the winnings are negative, then don't they have to reimburse you for those negatives? Well, it's gotta go
They.
somewhere.
I don't think there's anyone to bail me out.
That'd be a good fallback.
If you could do that, you'd be.
Buying this ticket is contractually obligated.
So when I do make enough money, I better do something about politics so that I can have some favors in Washington, so they can bail me out
Yeah.
when I only manage to sell all the winning tickets and none of the non-winning tickets. It's like, Uncle Sam, it's time to bail me out.
That'd be the percentage of money that you do get, right?
Well, actually, I'm not the one who asked for Uncle Sam to bail me out because I have insurance. It's my insurance company that's going to be asking Uncle Sam to bail them out. It's called risk management.
Push it downhill.
Yep. So, are there any questions about this particular problem? No questions? Okay. All right, so if there are no questions, I am going to go back to the class material because I just want to formalize what we have talked about in this particular homework description here. So we'll go ahead and start from the beginning, which I kind of skipped in the previous class. Okay, so probability is basically the studying of the likelihood of something happening. Okay, and the general form or the usual notation is P in parentheses X. X describes what you are interested in, and then Y is the actual probability. Y as a probability is always going to be a number between 0 and 1 inclusively. If it is 0, that means the probability of that thing happening is none. There's no way it can happen. If it is 1, that means it's 100%, which also means it is always going to happen. Okay, so why do we care? The bottom line, if you really think about it, the studying of probability, most of the time it has to do with money. Okay, what are the chances that this is actually profitable to do something like that or not? Okay, it's basically the bottom line is, is it worth doing it or not? Sometimes it's not money, and other times it is. Okay. What kind of company do you think what kind of companies is interested in probabilities?
Casinos.
Insurance.
Casinos, okay, but with casinos, they are almost always winning. Okay, so they don't have to do a lot of studying or research.
Horse races.
Insurance.
Horse racing, insurance, okay, very good. Insurance is big on probability. Why?
Because it's for premiums and charges.
Well, exactly, because they need to know how much premium to charge you, okay, charge a driver, charge a homeowner, depending on the risk factor of that client. If that client has in a high risk group, they charge more. If that client is in a low risk group, they charge less. But the only way that they can tell without a crystal ball that can show them the future is probability. Okay, so that's why probability is important in insurance business. What else?
Polls. Poll companies.
Poll companies, yeah, but that's kind of an interesting one because they are not using probability to make money per se, but they are using the publicity to make money.
Well, they can get endorsements after the publicity or whatever.
What else? What else is important in terms of probability? Think Amazon, think YouTube, think all kinds of social media. Why do you think they are also interested in probabilities?
Security.
Security, maybe.
Ad deployment.
Advertising, okay, but how does advertisement tie to probability. Yep.
Well, when you're trying to price ad spaces or people who want to buy ad spaces, you have to have probabilities behind like how much they'll make, like in the grand scheme of things, how much they would make from having that ad there, and then you can price that space.
Exactly. Okay, because if you go to Amazon, they will, and you're browsing through certain items, they will also show you, people who view these items or people who purchase these items also purchase blah 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 blah. Okay, but they only have so much space to show you those items, so they have to prioritize and not give you a list of 20,000 items that other people also bought because you bought a pencil, right? Because you're looking into buying a mechanical pencil that is $5. Okay, so they have to prioritize and figure out, okay, what is going to be the most profitable way for me to use this space and prioritize this item as the first item on that list.
Don't they use machine learning for that? They use machine learning for that.
But machine learning is probability.
But machine learning is, guess what?
Probability.
Yep.
And that's what you're
Based on
learning.
probability. Yep. So that's why probability is important. Okay, what we do here is not quite sophisticated as machine learning and stuff like that, but it is a foundation. Okay, these are the foundation concepts of figuring out other types of probabilities. As far as I'm concerned, I can also use probability to find out the likelihood that the answers of two multiple choice exam submissions have exactly the same wrong answers. Okay, they can have the same right answers. I mean, that is no indication whatsoever, right? Because people can have exactly the same right answers, but if the wrong answers are wrong exactly the same way, then I'm going to look into it and go like, okay, what is the probability of these things being the same wrong answers? But it has to be relative to the whole class, because it is possible that certain wrong answers are more popular than other wrong answers. All right. And the last paragraph is just my own spiel to the importance of understanding uncertainty. There's one great physicist who said, God does not play dice. Who was that, and in what situation did he say that? Einstein said that, and he was referring to quantum physics. Yep, because quantum physics is all probabilities, exactly. Now, there's a big difference between the probability distribution in quantum physics and the probability that we're dealing with in this class, because the ones that we deal with in this class is discrete. It's not continuous. Okay? But the probability that you're dealing with in quantum physics is continuous. So, which is kind of an oxymoron, because if you think about it, quantum physics is quantized, right? So how can something be quantized and yet it is not discrete? It is actually continuous. It's because space itself is continuous. Okay, the particle, the location of the particle can only be at certain places at any particular time, but the location, the xy coordinate, the x and the y and the z, those are continuous. So that's why it is both quantized and non-discrete or continuous at the same time. Yep.
Does making a probability problem discrete, does that kind of ease the math? Like, it just seems that it would naturally, that it would be a simpler problem to solve a discrete problem as opposed to.
I wouldn't say it is always easier, because there may or may not be a closed form when it is discrete. The only thing about discrete is well, we'll talk about exactly what I mean by discrete. Okay, so we'll go through this just a little bit, just so that we know what is the difference between discrete probability as opposed to continuous probability. Okay. So in any way, P is a function. Okay, uppercase P is a function that maps a set of events to a number that is either that's between 0 and 1 and is a real number. Okay, that's basically how we deal with how we denote probability. In the case of something that is continuous, if you have an element A in D, you have another element in B in D, by definition, if D is a space or a set that is continuous, you can always find something C that is between A and B. Okay, you learned this in calculus already. Okay. On the other hand, when you're dealing with discrete probability, then you're dealing with something like this, getting 2 or more tails in 5 coin flips. Okay? That is a probability, but the number of tails in 5 coin flips is discrete. You can have 1, 0, 1, 2, 3, 4, or 5. There are only 6 possible cases that can happen. Yep.
I don't know if I'm thinking this wrong, but from that description, is it wrong to say that like the set of integers also fits that description? Because if you take any like A and B from the integers,
Well,
and
the
you
set
require
of
B
integers
and
is
B.
infinite, so that becomes a little bit tricky.
Unless
Because you
isolate
can't have a B
specific
technically.
integers.
Because technically speaking, the probability of choosing a particular integer out of all integers is 0.
Yeah.
Because you have an infinite number of integers.
Okay.
So when
That's
we're dealing
kinda
with
weird.
discrete probability, we are looking at a finite set as well, because otherwise it makes no sense.
I'm not gonna lie. I'm kind of confused by that. Like, how is it 0? How is there a 0?
Divided by infinity.
It's 0.
It's 0.
Yeah.
Yeah, the bottom will
You go. Yeah. Okay. You're right. Thank you.
Or it's more like 1 divided by a number that approaches infinity gives you a number that approaches 0.
Yeah.
Yep. Yeah, this is really kind of interesting because today I went to the second design committee for the replacement building for the liberal arts area, and right now they're talking about having physics and engineering moving into that building. Not only their classrooms but also their faculty offices, which I can kind of understand. Where if your office is a long way from the classrooms, that's really inconvenient. So having them in the same building actually kind of makes sense. But one of the idea was they can have more time to spend with students, so they can basically be walking along the hallway and bump into students and they can answer questions. And I told him, but I'm already doing that for you. in some cases, yes. But it's going to be one interesting building because they're going to roll many different subject areas into one. So math is going to be there, physics is going to be there, computer science is going to be there, which is probably good news for most of you because you're taking classes from all 3 departments already, so you can stay in the same building and not having to move most of the time.
lead to obesity and
Sorry?
And then you get
lead to obesity, moving less.
Moving less, yes.
Burning fewer calories.
Exactly.
Well, it's going to be a multi-story building, so maybe that will help.
Unless they throw in a bunch of
You
elevators.
can always help a professor to move equipment, up the stairs and down a little
The
bit.
manual way.
Yep. And we were also talking about how to configure the classrooms. And I mentioned, in my classes, I try not to use the whiteboard as much as possible and just, do everything on the projector because it's all going to be screen recorded. Apparently, that's not how math professors do things.
Rather the
I
opposite.
wish.
They prefer the entire classroom to have whiteboards around because they like to write, write on the whiteboard, all the way around the entire classroom.
Yeah. They do.
Get a little scooter to roll
Sorry,
around.
go ahead.
That's the worst. Because if we could record like every math lecture, I would be doing a lot better in my class.
I suppose you can still do that. Do people actually in a math class where things, stuff is written on the whiteboard, do they just, kind of pop up a cell phone
Yeah.
and take pictures?
Yeah.
When the teacher allows.
Oh, when the
Kinda look
teacher
down.
allows.
I mean, but I feel like
Teachers can
that's
say
all
no.
on the internet.
When he turns
'Cause-
around or something.
Well, unless you got the flash on, that's gonna be real noticeable real quick. 'Cause some teachers, a lot of teachers believe in the whole if you write it down, you remember it better, which
Which is the truth.
99% of the time is the truth. But so
Okay.
they don't want you to take pictures of it. And
Okay, so let me
secretly
just
like-
repeat your point. So the point was, if people write down stuff in a class, they tend to remember and understand the material better. Okay,
That's not
so
true.
that's
Ooh,
okay.
that is very
You can't
But
say it's
my
not
question
true.
is it a causal relationship or is it a correlation?
Oh, correlation.
So it's possible it's a correlation, which means motivated students who are going to who want to understand the material, they are the ones who are writing down the notes.
Yeah.
But it's not because of writing down the notes that make them good students. It's the other way around.
Yeah.
They write down the notes because.
But I don't know whether the answer is that way or not. Okay, I'm just
Yeah.
putting it up as a possibility. Yeah.
In some cases, like I find, especially in my math classes, when they're moving really, really fast and you're copying all of this down, you don't have the time to really think and hear what they're saying versus just trying to write it all down.
If you
And
don't
then when
know
you
what
go
it is
back to
when it's
review
on the
all of your
board,
notes later,
it's not
you don't have
No idea.
the context that
Mhm.
was spoken.
Yep.
So like, yeah, I can remember what I wrote down, but I can't remember the context.
But would you say that's going to be much more beneficial than if you sat there not understanding?
Well, I
what
take
you
notes
did?
anyway, but if
Yeah.
I'm able to go back and watch the video, then the context is there.
It would be nice if the whiteboards had some sort of sensor in which detected what the professor was writing and then wrote it to a file.
There are such whiteboards. They're called
Smart.
smart boards. They do exist, but they are costly for one thing, and I think the technology is not 100% mature.
And you know what's funny? We had that in of all classes, which did not need it. I had that in my philosophy class. Like the
Yeah.
philosophy professor used a smart board.
They have them in the automotive department.
Like, what do you do?
Let's
Go
test this
ahead.
on the people who don't use
Can you
it.
explain the new homework assignment since we just did the old one?
Yeah, I'm gonna give you a new homework assignment.
Okay, so
Yeah.
it's not gonna be due. Do you know what it's gonna be?
Well, it's not. I'll give you guys a week to work on it. So if it is available on Thursday, then you have 1 week from Thursday to work on it.
That's good. I like
All
it.
right, so this is an important one because we talk about discrete probability space specifically. And it's basically, this is a construct to model the real world in terms of probability, but only when things are discrete, okay? The probability space has 3 components. Omega is the set of all possible outcomes of what is being modeled. So in the case of what we just worked on earlier, omega is basically the set of all possible tickets. And we have 3.5 something million of those tickets. Is that okay? So omega has 3.5 million elements, each element being a possible ticket in that particular system. And I think this is a F, and let me just double check, make sure. Yep, so it's just an F, but it's a kind of like a special font.
Fancy, yeah.
Yeah, fancy. Yeah, F for fancy. So this particular set is a set of events. Okay, now this is kind of important. An event itself, which is an element of F, okay, an event itself is a subset. Okay, so it is a subset of elements of omega. The union of all these elements in F should be omega itself. Okay, so let me just kind of throw this out and see if you guys actually get the idea. Okay. So let's say we have omega being a set of A, B, and C. Okay, that's perfectly okay. I can just say that A is one particular possible outcome, B is a possible outcome, C is a possible outcome, and we only have 3 possible outcomes in omega. So in this case, when we get to F, okay, can someone name a particular element in F?
Okay.
Okay, so can you give me the actual punctuation as well, not just A? Do you mean that? Because each element of F is a subset of omega. Okay, so A by itself is not a subset of omega. A itself is an element of omega. So it is important to make that differentiation. Okay? So what about the other one? I can group B and C into a subset of omega and make it an element in F. Now, when you look at all the elements in F, each one is a subset of omega. But when you take the union of all of these subsets, we get omega back. That is what the note is saying. Is that okay? Because this is really an important concept, that F itself does not have elements of omega, it has subsets of omega. Is that okay? All right. So F is the set of what we call events. So in this case, A all by itself, which is a possibility, is by itself an event. B, C is now grouped together as one particular event. When we talk about P, it is a function that does not use omega as its domain. It uses F as the domain. So in this case, okay, using this as an example, P as a function is going to be two tuples, right? Exactly two tuples. How do I know it is exactly two? How there are only exactly two elements in P?
Two elements in it?
It's because of the domain. Which one is my domain again? F. F has exactly two elements. But each element is a set. That's okay. There's no problem of using a set as an element. Okay? So in this case, if I have A, the set of A being the first element or the first item of the first two tuple, and I assign the probability of 0.5, 0.3 here, what do you think this one has to be? Has to be 0.7, because when you sum up all the values, they have to sum up to 1 exactly. Very good.
No.
Yep, go ahead.
This is just an example, right? Like if
It is just an example.
If that was our actual omega, wouldn't F have more elements, or would that be the actual? Would that be all the elements of F if that was our actual omega?
Yes.
That would be it.
Well, this is one way to partition.
Okay. Oh, okay.
This is one way to arrange, F. You can have F being, okay, now, I can give you another example, okay? F is just basically events that we're interested in. It is possible that this is something that you're interested in, okay? The probability of none of those, possibilities happening can still be something that you want to track. It maps to 0, but there's nothing wrong with having the empty set as an element of F. That's perfectly okay. You can have A, B, C grouped together, which is not very helpful because the probability of one of those three happening is exactly 1. Okay, because that accounts for everything that can possibly happen, right? But this is one way to arrange it. In other words, how you partition omega and break it up into subsets into F depends on what you're interested in. Okay, for instance, in our example, okay, you can basically say I'm interested in not winning any money is one subset of omega, okay, of not winning anything. Winning $12 is another subset. Winning $60 is another subset, and so on. That's one way to partition it. You can also partition it as, what if I just want to know whether I win something or nothing? Then you only have 2 items in F. One being the subset of all the non-winning tickets, the other one being all the winning tickets. But it all depends on what you're interested in, okay? What are you trying to figure out? Is that okay? All right. So this is really just notation, at this point. For a probability space to be discrete, omega itself has to be countable, okay? Which means, the cardinality of omega has to be this particular symbol. Have we talked about this before?
We
did, because we mapped everything to natural numbers.
But it didn't have the 0.
Yeah, the 0 is just indicating that it is starting with 0. In many cases, omega is finite. I think it has to be finite to make sense. It doesn't have to be finite to make sense because you can have an infinite number of elements having a probability of 0. So you can still have some sense out of a omega that is by itself infinite.
What does that symbol mean?
Which one?
The curly N?
The curly N? Okay, the curly N actually has a name.
Aleph, no?
Yep, Aleph. It means, okay, when you see this symbol that the cardinality of a set is, aleph, sometimes it's aleph subscript 0, it means there is a way, there's a bijective function to map omega to the set of natural numbers.
Sorry, one more time.
Infinitely.
Okay. When you see omega, or the cardinality of a set, in this case omega, equal to aleph 0, it means there is a bijective function mapping omega to the set of all natural numbers, which we are very familiar with because of the exam.
Yeah. In the 3D space.
And the homework assignment to fold 3D space into one. Yep. So that means the cardinality of 3D space, where coordinates are all natural numbers, is actually just aleph 0. It's not any worse or better than just natural numbers. Okay, any questions at this point? Does anyone want to figure out, what are the chances that you get one tail out of 5 flips?
One tail out of 5 flips?
5 coin flips. So if you flip a coin 5 times, you get only one tail and the other 4 are heads. But the ordering is not important.
Yep, the permutation.
Like, what are the chances of that happening?
One-
What are the chances of that happening?
1 out of 2 times.
Sorry?
Exactly.
Exactly 1. But it can be the first flip, can be the second flip, can be the third, can be the fourth, can be the 5th flip. So think about this, and I will address that in the next class. So
He's
it's not
already thinking about what is this?
It's not a homework assignment, but I want you to kind of think about it. But you want to think about it in these terms, okay? What are all the possibilities? And of all the possibilities, what is the subset that you're interested in?
How many coin flips did you say? Yes? How many coin flips?
5 flips. Out of 5 flips, I want exactly one of the 5 being tails.
Oh, so you want a combination where 4 of them were heads and 1 was...
Correct. And